Hello, my friends. Greetings, my RF and microwave design professionals, research students. Today, I'm gonna go ahead and continue my series on the design of KK band SATCOM receiver, or might want to call it low noise block down converter because it's in conjunction with the indoor modem, it becomes a complete receiver. Um, just to remind you, um, we uh, the first here's the first part, and the second part are online on my YouTube channel. I would urge you to go ahead and visit my YouTube channel at this link here. I would appreciate it, or just type Dr. Mohamed Nezami on the search engine and it should land on the YouTube channel. Be sure to visit and please sign up for the channel so you can get updates. This series, if you're just happening to watch this video, as a prerequisite for this video, please you need to watch part 1 and part 2 of the series. So today we're gonna continue on part 3 of the series. And today, basically, what I have is I have here's my system view design tool. And what I did is I'm just implementing the converter in here, and I'm just going to review all the results that we're going to get as far as how the down converter is implemented. As you can see here, this is a chain budget link calculations that you can estimate all these things. So and then I did a sweep on the front end of the down converter, basically dual band down converter. Okay, and I'm going to go through with the theory in just a moment. But the implementation starts out with the SATCOM signal being generated in the signal generator in here. Then here's the LNA, and then I have a two-channel selection of the low band or the high band. And then at the same time, when you select this, you also select different set of PLLs, phase lock loops, as a local oscillator. You have the low band and the high band LO. And so both, and then of course you've got the common IF section in here, okay? So let's go ahead and start this. So I'm just gonna go ahead and start this. So like I said earlier, we're just gonna go through the block diagram today. In the previous sections, we went through the topologies, different topologies of the design approaches, and we ended up with one. So we're going to start with a hand sketch of the that I did for the complete SATCOM K band front end of the receiver. And we're just going to implement that in a block diagram at the system level. But all of these system level blocks, they're really linked to a model. All these transistors, amplifiers, filters are linked to a model, or either a small signal S parameter file or a nonlinear large signal model. Okay. And so we're just going to go through the selection of filters, the sweep the front end for the common way of displaying the gain as a function of frequency, and the noise figure as well. And we're trying to reach, remember the noise figure that we're trying to reach to be competitive is somewhere less than 1.5 dB. So, which puts a constraint that we have to have a front end LNA that is sub 1 dB noise figure. And then we're allowing a half dB for the rest of the system as contribution and the waveguide to microstrip transition. Okay. Um, now, I did mention my name is Mohamed Nezami. I decades of RF circuit designs in the USA with major companies, and I'm operating currently from my semi-retirement um, home back in Jerash, Jordan. I operate very inexpensive, so I'm able to actually work for as low as $20 an hour on some projects. If you happen to have any designs that you would want to offshore, offload your company from and send it to me, I can design that for you. I start out with you give me the concept, I work with you on creating the specifications, and then from specifications, I work with you on the system architecture, model using MATLAB, HFSS, ADS, System View, and other proprietary RF and microwave design calculators. And then I actually draw schematics and give you a BCB done, complete, ready for fab. Okay. So if you have any projects, be it low noise amplifiers, power amplifiers, GaN power amplifier, um, front ends, filters, whatever it is, we can work on it for you. Okay. All right. So let's just review from the past two video sessions that we have. We're interested in the receive portion of the both military and civilian Ka band SATCOM receivers, downlink. Okay, and the downlink is allocated to these frequencies, roughly from 17.2 gigahertz to about 21.2 gigahertz. Sometimes they go as far as 22 gigahertz, some bands, and they split like this. We realize this. The low band is for commercial use, and the upper band is for military use. Of course, unlike the KU band, the KU band is lower in frequency, which is easier to work with. And you can see the KU band downlink for LNBs is down here between 10 and 12. Okay. And of course, as most of you know, to separate the receiver from a transmitter on these SATCOM terminals, the frequency division duplexing is really great because, for instance, in KU band, you transmit between 14 and 14 and a half. You receive from 10 to 12 or to 13, which gives you a gap that is good enough to obtain isolation physically, so you can have reasonable size equipments, be it the waveguide assemblies and the printed planar circuit assemblies. Same thing for KA band. Now, what's interesting nowadays, of course, we've got the 5G band from 24 to 29, and everything I'm going to talk about really applies to these bands as well. We can utilize all the techniques that I have for building a base station or a small cell site for the 5G market, even though the 5G market, of course, a lot of the receivers and antennas are planar and not parabolic like the case in the Ka band. Although the Ka band recently started, a lot of systems are on the move, and they're planar actually. Okay, so last time, this is a hand-drawn generic low noise block receiver or a front end of a receiver, okay? That this is the outdoor unit, okay? That converts from 17 gigahertz to 22 gigahertz down to 950 to 1950 or 952, as we will see, 2950, for instance. It could be either a gigahertz or 2 gigahertz bands. This goes down to the indoor unit, which has the modem and of course your user interface application to equipment. Now, while you're sending down the RF signal, that has the modulated signal down in this band downward, there's also from the indoor unit comes up the transmission line up here is the DC, because we really don't want, when you look at these, this is just, I picked this as an example from one of the manufacturers. This is an LNB, typical LNB, waveguide on one side and then SMA or N or F connector on the other side, which is this side here. Now, obviously, you don't want electricity connected here. So what we do, we send the DC up through the cable that brings down the RF, and this DC gets blocked from going this way, and it comes this way, where we regulate and create all the various voltages needed for all of these sections in here. And along the DC, we also send up the 10 megahertz reference for the generating a local oscillator signal that will beat or mix with the incoming signal so you can produce an intermediate frequency, IF frequency, as we call it here. Okay? Now, why is 10 megahertz sent up? Sometimes some systems, they have actually a separate input for the 10 megahertz because they may have GPS receiver, or they may have a separate system that distributes the reference to all of the equipment, such as the platforms and ships and so forth. And usually I put down here is the frequency plan to receive from 17.2 to 22.2 gigahertz. They're usually chopped up in sub bands. And when you buy these, you really have to specify what frequency you're interested in. Where are the channels that you're going to be operating on? So you look through these, and depending on that, of course, these will have different LOs, local oscillators. And then, of course, the IF is the same for all of these, because obviously you want to use the modem doesn't change the input frequency. It's fixed IF frequency standard, which is this frequency band here. Or some of them may come with 950 to 2950, like the system I'm going to propose today. So this is the frequency plan for the way they do it in industry nowadays is they chop it into 1,000 megahertz or 1 gigahertz bands. All of them have the same IF, 950 to 1.95. And then, of course, all of these will have different LOs, as you can see in here. The LO is either the LO that is needed really to produce this frequency or one half of that. Because remember that in the design, these mixers, we can have them with an internal ×2 frequency, that Doppler frequency. So, or it's a subharmonic mixer. So we can actually design this feedback loop circuit in here at one half of the frequency in this range instead of being at this range, which is more difficult to implement. Okay, so to the system that I'm gonna build, I'm basically proposing that I'm gonna build this system in here where I chopped up the band into two halves. Instead of these numbers, 2, 4, 5 bands, I'm gonna have only two bands, okay? First band from 17.2 gigahertz to 19.2 gigahertz, and the second band will cover the rest of the band to reach out to 20.2. The LOs are fixed either this frequency here or this frequency here. I'm going to use a mixer with a Doppler so that I don't have to operate the local oscillator at these frequencies. The IF that I'm going to use is a little bit wider. And of course, if you happen to review the modems, SATCOM modems from all these, Tampa Microwaves or iDirect or some other ones, there are a lot of modems that are advanced modems that can accommodate this band. Okay, this is a full 2,000 megahertz band. Okay, now the image frequencies. Okay, the image band, while we're receiving 17.2 to 19.2, of course, we got the image in here, which is 13.3 to 15.3. That will also mix with this LO and end up in this band as well, with spectrally inverted, of course. This is an issue, so we have to filter that, okay? Now, just to remind you, I'm not going to teach the basic concepts of receivers. The image is has to be rejected so that we can reject the broadband white noise at these allocations. Otherwise, this noise will fold back into in band and will produce will double the noise figure actually. Okay, so these images in here, what they are really, depending on whether you're going to have a low side LO or a high side LO, it's going to be on either side of the RF signal. Either it's going to be below if it's going to be above the received signal or below the received signal. In either case, so the image will be either on the other side of the LO by exactly the same IF distance. Okay, now again, we're trying to beat the LO with the desired signal and produce this IF. But what happened is that this here is an interference, which is the image frequency. It's going to beat also with the LO and end up here, except it's spectrally inverted. So that what that means is the lower side frequencies of this image will be the higher side and vice versa. So that's why a lot of times if your noise figure on your low noise block is deteriorating on the upper half versus the lower half, and you try to troubleshoot your image rejection filter, it's very confusing because of this fact that the image is translated inverted in frequency. Okay, so that's what this means is the image frequency. You can go back to some of these basic receiver books, and it will show you what the significance of all of these things. This is typically what the specifications Ka band low noise block down converter specifications that we have here. So I'm going to build to this, okay? And this is really, if you check out the dominant companies for the Ka band SATCOM equipments, be it Swedish Microwave, XMW, or some of the other ones, Gila, wherever, you will see that most of them are basically coded this. So the input is usually WR-42, which is the waveguide that is from somewhere from 17 to like 24 gigahertz. And we went through this in the part one and part two, showed you that interface. So part of the design we have to design is that this low noise block in here, we have a transition that will be from rectangular waveguide WR42 to a strip line, or either using a printed probe on a trace that goes down into the waveguide, either inline or orthogonal, and will pick up the signal. So, and that part is critical. And in part one and part two, I went through that. I have in my channel designed those transitions from waveguide to printed microstrip lines. We're going to pick one of those, okay? So that's that. And then, of course, the rest of the stuff is all going to be complied with. And we're going to try to today in the block diagram that I have implemented on system view, we're going to try to check if we are within these specifications to simulate as much as possible to try to make sure that we are close in performance to these, so that when we actually start building schematics and putting down all the components, real components, we're not going to end up with some issues, okay? Now, just to remind you back, the 5G frequency bands, in these regions of the world, they're in these bands in here. So everything we're going to talk about really applies to the low bands of the 5G systems. Everything can be used. First thing is the critical part in here from last time. And please, if you're watching this again, as a reminder, please, this part, please go ahead and go back to part one and two, because otherwise you're missing a lot. So one of the critical components we have is this. It's the mixer. Okay, what type of mixer how we're going to translate the frequency from this band to this band. So we chose that as a mimic part from one of the semiconductor manufacturers. This here is a discrete, like we have concluded in the previous part that we're going to build this using discrete transistor MOSFET parts. The IF section in here, we're just going to pick mimics and ceramic filters. The phase lock loop is a chip from TI or Analog Devices. We're going to pick that up. And of course, there's mimic and ceramic filters, mimic amplifier and ceramic amplifier filter that cleans out the and level shift the carrier out of the PLL. Okay. Now the rest of the stuff is basically these are regulators, DC to DC regulators. We're going to pick those from TI or from Analog Devices. And the 10 megahertz section, there is really not much because this 10 megahertz comes in here, a strong signal. Sometimes we may have to build a driver to drive the level and assure the input impedance to the PLL chip. Okay, so the mixer that I have chosen as a start right now. And in the previous session, we went through a family of these. So what I'm going to do is I'm going to try to use a single sideband quadrature down converter, okay, which basically what it does, it takes the signal in as an RF signal, split it into two mixers that are driven with a quadrature local oscillator signal. Okay, the local oscillator signal, I get the reference 10 megahertz, and then I create a carrier using the phase lock loop system in here, which is a set of chips. Okay, and then I feed that into at a half of the frequency that I would need to translate this down to this level here, so 2950, 950, 2950. So which are two values in this case, which I mentioned in here. They're in my frequency plan. They're basically 8.125 gigahertz and 9.125 gigahertz. Okay, so I need to generate these in this PLL, either a single PLL to cover both of them, or two separate PLLs. Okay, this is yet to be determined. Okay, this is going to be a whole part on my series. Okay, just to design this portion here and system analyze it. So we come in here at one half of the frequency that I would need, which is half of 16.25 and 8.25, which is these values. And these are so close to each other that you can do them in one PLL chip, okay? And so I come in here, this gets internally, it has a DC block. Of course, there's DC blocks on all the ports except the IF. The IF is DC coupled so that you can have direct converger receiver if you want out of this. So I come in here and double the frequency, amplify again, and then of course you go in a quadrature hybrid, 90-degree hybrid. There's internally terminated on the oscillator part. And then this LO drives both mixers. And what you end up with is a quadrature I and Q, which in this case they call them IF1 and IF2. So I'm going to take these two that are 90-degree shifted from each other, their quadrature, and then use a 90-degree hybrid, external 90-degree hybrid to actually get cancel out one of the single bands, okay, and get a single band signal in here, which is the IF that is in this range. And then I'm going to use an IF section to amplify it. Of course, the images are in this image here and this image in here for both the bands. I need to build a bandpass filter, this bandpass filter in here. Now, realize this is really image rejection filter, image rejection mixer. Okay, this technique in here. It's single sideband, but still though, I would still need to reject the image in here. If you look at this chip, you will see that the image rejection on the single sideband generation process is in the 30 dB specified. But in actuality, when you put this on a board, with the quadrature impairments that you're going to get, you're not going to get more than between 20 to 25 dB of rejection on the image. So we're going to use an external microstrip filter in here that I'm going to design, which basically will band pass these here, these bands. And these are two different filters. I'm going to switch between two different filters to a common LNA. Okay, and of course the switching is done after the LNA, so it doesn't impact the noise figure, assuming that this is a gain of 30 dB, like I have it in here. Like I allocated, by the way, the gain is 30 here, 14 is for this guy here. He comes in with 14 dB amplification, and then 20 dB here, and that puts you somewhere between 55 to 60 dB of overall conversion gain. This filter in here is critical because it has to reject the image, and the image in here is specified with these values. I computed this in my frequency plan in here. If you look at my frequency plan in here, this is the image low and high, this band here and this band in here. So I have to reject these by at least 40 dB, which is doable with a macrostrip filter that is barely about 1.5 inch length, okay? Even less. Okay, so I'm going to start the system now. I'm going to go ahead. So I picked all the parts, and then I constructed the system in here. Okay, as you can see it in here on system view. Starting out, this is my SATCOM signal in here as a CW for right now, just like we would do on the bench on testing one of these in actuality. And then, of course, your LNA section right now is to be designed. Yeah, but I have figured what are the specifications for this LNA. I go through a switch in here that switches between these two filters. And then, of course, again, you switch back these signals in here into, this is a mimic bipad attenuator that will be used to just basically improve the isolation and return loss to the mixer. I go into the mixer, and then, of course, from the mixer, I have an IF section, which is made up of two filters that I will tell you in a moment what they are, okay? And then two identical mimic amplifiers, okay? And then I distributed about 4 total bipad attenuators. These I throw in everywhere so that I get good isolation and sacrifice a little bit gain, but they make the design easy. Okay, these bipad attenuators in here, they're made of basically discrete 0402 resistors, while this one in here, because it's a K band, this is professionally a mimic attenuator, chip attenuator absorber. And then what I did is these filters in here, I at the moment, I designed them using a block specified response, which is in system view, because I don't have this design yet. For right now, I'm just going to specify the shape and run them in the overall system to make sure that my system performs correctly. Now, where do I get the models for these devices? These devices in here, all the models, large signal, small signal, I get them from the data sheets, and the manufacturer provides files for these. So I get for the filters in here that you would see here, all these filters. The switch for right now is just a single switch with a 0.5 dB of insertion losses to be picked up later. Okay, like I said, of course, okay, the mixer now, the way I basically build the model, if it's not available, like in this case, I would just go to the data sheet in here, okay, and store this template in here in system view, which shows the frequency and then all of the various parameters that I'm going to use for this model. Like you see here, the input 1 dB compression point, I chose one single value for all of them, okay, which is a flat line. It may vary a little bit, but at this moment, I don't need to be more than that. And then, of course, all of this is really, there are some software packages where you can scan these images. For instance, in here, conversion gain versus frequency, which is this column here. There are tools that you can go to the extent of taking scanning this, and then it would give you actually these curves. For every one of these curves, it gives you a column corresponding to these values, or you can just do it by hand. And that's what I did basically, okay? Or you can do the mixer using the table in here. And so what I did in here, I have both models, and I ended up using the table model rather. I mean the data, the Excel sheet model printed in column and values, discrete values. But you can also you choose the table, the mixer table, which shows you the M and MN products of the local oscillator and the RF signal. So you've got the RF signal coefficients in here, and then you've got the local oscillator coefficients in here, and you got the mixing products, and they're all, of course, normalized to the IF. And you could choose either from IF to RF to IF or IF to. Let me just show you that quickly on the. So this is the mixer that I'm using. So you can see that the model for this mixer really right now is based on this here, okay, and on these discrete values in here. Where if you choose the model to be this one in here, this is another alternative, okay. And so this one in here, basically you've got this is the table. We're going from RF to IF, and these are the values. And where you get these actually you get from the data sheet. Okay, so we've got the mixer data sheet in here. You can come in here and either extract from here, or it does actually give you a table. And of course, you want to make sure that you have the same condition, the LO level and all of that. So you can see here how the M and M time N spurious output model you can use this and enter it into the system view model to give you that. Okay. Okay, now to the image rejection filter. Image rejection filter, as you can see, now it depends. You can have two filters that have some dead zone, or you can have two filters that actually overlap to each other, and that's what I chose in here. Now, here's the catch here. Now, there is some people, if you look at the SATCOM equipments, in some cases they use, like I use here, a switch between bands, or you could actually use a two-way splitter in here. You can use a two-way splitter and a two-way splitter in here, and that way you don't have any switching mechanisms to reduce to which will become critical and may have some issues. Okay, but I chose to do it this way. So we've got the two bands. So basically, from 17.2 to 19.2 for the red curve in here, and then from 19.2 to 21.2, okay, for the blue curve. Of course, my image bands are setting between marker 1 and marker 2 and marker 3 and 5. And you can see that the highest frequency, we're up in the, let's see, 5 here. That's minus 40 dB. Okay. Now, minus 40 dB, the overall image rejection specification that we need is specified image rejection is 40 dBc, okay, minimum. And so in this system, since we have some image rejection from the single sideband operation in conjunction with this filter in here, so we will be good, okay? We're saying 40, but we may not get 40. So in that case, we still have a headroom of about 25 dB or so. Now, remember, some people may argue and say, well, this single sideband receiver in here doesn't need an image filter because the design specifications calls for like 27 dB. In some systems, it may work, But in this case, no, we are really trying to achieve extremely low noise figure. We're trying to achieve an overall noise figure of less than 1.5 dB. For instance, if you were doing this for 5G with strong signal for a radius of a few kilometers from the base station, you might say, well, I can have 3 dB of noise figure, and then in that case, you may not worry, and then therefore you may not need a front-end filter, critical filter like I would here, okay? Unless you, of course, you're trying to, assuming that you don't have, your antenna is not going to be picking up interferences. Now this filter in here, I'm going to design it using microstrip, and I did design one for a customer in New York about a year ago, which worked really fine as part of a Ka band system. But in my early on, I started to look around and seeing if you could consider some of these filters that's starting to come out, like for instance from Knowles, Director Clap, with a red curve in here. That's a nice filter that they sell right now, but it's very expensive. It's like $100 to $150 a piece. Plus this one here, by the time you really get it to work on the board, all the parasitics, the grounding issues, the isolation issues, it becomes a headache. So I chose to just go ahead and design my own. There is a filter for Ka-band SATCOM system available from many circuits, GasFit mimic based filter. You can see it in here. It's a bit wide, and I can't really use it. Maybe they did it so that maybe for 5G, but it's not going to work for me. Especially the loss is excessive. It's nearly almost 5 dB loss. Okay. Now, if you're interested, this is the part numbers for these two parts in here. So this is, again, a system that I did earlier last year, and it did work fine, beautifully, although this one has still got a little peak that needs to be worked on at the time when I did this, of course. And you can see here it is. This is edge-coupled filter from the connector to the first mimic, and it worked beautifully for this band. Okay, the IF section in here is basically made of ceramic filters that I picked commercially available, and they're cheap. They're $1 each. And then a mimic amplifier from Curvo. So these are very available from Mauser and so on. Okay, and then of course now the IF filter. Now, this was an issue because what I really want my IF according to my frequency plan, which let me go back to it. We're trying to cover from 950 to 2950, okay? To 950 megahertz to 2950 megahertz or 0.95 gigahertz to 2.95 gigahertz. We're trying to cover this, and this is really an awkward band because most of the bands are done for the 950 to 1950. If you were operating like that, there's plenty of devices out there. But for this band here, it became an issue because when I grabbed, for instance, I grabbed a bunch of these from one manufacturer, although these are available from Johansson, from Murata, and from many circuits as well. All these ceramic and integrated LC type. This is a lumped component bandpass filter, and this is a ceramic filter. You can see that all of these I can't really cover to 2950, but they work beautifully from 950 to 1950, okay, which is the most common. That's what, as you can see here from my oh, well, no, this is for the new part I'm proposing. But for conventional low noise block IF converters, usually 950 to 1950, it works really well, all these filters. So I did more search, and what I realized I could really, of course, we've got some low pass filters that can extend to 9 gigahertz, and we're going to use these for the yellow section that will come later. We're going to talk about, but I looked at the low pass filters in here. So there are plenty of low pass filters that we can utilize to fulfill this 950 to 2950 megahertz. And so what we're going to do is to reject the lower frequency. I'm going to combine a low pass filter with a high pass filter. So what I did is I located few of these low pass filters that start out from 950, which is really good in here. They reject this band really well. And I'm going to combine a high pass filter with a low pass filter like this. I'm going to use two of them. And that's basically what I did. And these are the two parts. There's two options in here, which will give me a nice bandpass filter on the frequency band that I want. This way, I don't have to design my own IF lumped component filter, which is terrible to design, considering the tolerances of capacitors and inductances at the 3 gigahertz bands. Okay, so this is basically, let's see, we mentioned this. Now, the other issue that I have is, of course, is the quadrature, the 90-degree quadrature that I would need here in this mixer. Now, by the way, I forgot to mention the mixer model that I use in here is really based on the mixer model that is in the data sheet, which assumes, which was measured or constructed using an external 90-degree hybrid. Okay, so I know this is a critical issue. So for right now, I'm designing this based on the data sheet, which uses a specific 90-degree hybrid in here. If you go back to the mixer, let's go back to here. This here, the manufacturer used one, and actually the model that I get is actually is encompasses these here, and it assumes. So what I'm doing right now, all the model that I'm constructing is assuming that the hybrid that I'm going to pick has the same performance, which it is not for sure. Now, these people here, they must have used a 50 ohm connectorized, probably 90-degree hybrid that is very expensive because broadband and really well matched in quadrature. So I can't have that luxury, of course. So that's an issue. But for right now, let me just assume that I'm doing exactly what they are doing. And then, of course, later on. But looking at early look at this, looking at the Zinger parts at a 90-degree, which is really tiny, 0805 package in here. So as small as a little capacitor with this package in here. If we look at these tolerances in here, and they give the tolerances between 700 to 2700 megahertz. Of course, I'm not operating in these bands here. I'm operating a little bit more than that. Okay, but this really puts you out the quadrature gain errors and phase errors. They put you out somewhere in the mid-20s of image rejection. Okay, which is really that's okay, because in my case, I'm using an image rejection filter ahead of that. Now, I did import the S parameters for this quadrature, which is this part here, this part here. Okay, and this is basically what it has. Okay, and you can see here, this is the isolation and this is the quadrature ports. Okay, and you can zoom in actually and look at the band further, and there are some issues that I'm going to have. So this is one thing. But if you were using this for 950 to 1.950 or 1950 to 950, if you look at the, and I did this diagram in here shows the quadrature phases difference, the phase error and the gain error. And you can see that it's pretty good. Considering, it's only like up to like 2.7 degree error, and the gain is just about 0.2 dB error. And if you go back to this standard formula plotted that shows the if you are 3 degrees of phase error versus 0.2 of a degree, you're out here somewhere, which is very good for that one. But of course, in my case, I'm really using this device to go from 950 to 2950, in which case in here it flares out in gain error. So I'm going to have some issues in here to solve. Okay. Okay, let's head on to system view and start looking at this. So I have this built up, constructed, all the models, all they were scooped into the system, and I'm going to put in a system where one feature, the low band, is basically go from here through this filter in here, go out here to this common IF, and then the LO is going to be switched. So this is the low band LO. Okay, and the low band LO has the value 8.125, where the upper band is 9.125 gigahertz. All right, so we're gonna look in this, and I'm gonna do is sweep, look at the frequency response, the overall frequency response, convergent gain, I mean, that's what it is. And then I'm gonna sweep the complete system, fixed LO, sweep the RF input level in, and compute the noise figure and gain and other parameters as well. And then I'm gonna also sweep the input power level to see the dynamic range of this receiver. Okay, and that's what I'm going to get next. First thing is we're going to look at the budget link throughout the whole system in here, and that's what's plotted in here, as you can see. And what I have in here, I have the DCP, which is desired channel power. I'm putting in minus 90 dB right now into this signal generator in here. I'm putting minus 90 dB. Now, minus 90 dBm. Minus 90 dBm is typical because you've got a parabolic dish or a flat panel antenna that gives you about 30 dB gain. So that puts you down in the minus 110 to minus 120 dBm signal levels that are typically is the power spectral density of the SATCOM signal on the Earth. Okay, so from minus 90, you can see how the desired signal gets all the way to, amplified and converted until you get minus 20 dBm, which is beautiful. That's exactly where I want to be. The typical modems, they can operate from minus 10 dBm to anywhere minus 35 dBm mostly, typically. And of course, I have the cumulative gain in here. You can see that the gain is 68 dB, which is good. I don't need that's high gain. That's almost 70 dB, but we're going to allow 8 dB of loss through the entire system in here. There's lots of losses that are unaccounted right now, mismatched losses, ohmic losses, and so on. So you always want to over design your system by at least 10 dB. And of course, we got the luxury of these bipod RF attenuators that we're going to throw in that can actually damp down the signal level to just in case if we end up with higher gain than we would expect. The noise figure, which is the most critical part, is 1.023 dB. Okay. The output 1 dB compression point is 11 dBm, which is very good. That's typically what we want. Although, let me see, I think on the specification that we looked at earlier, let's see, the output P1 dB, output P1 dB plus 5 dB. Okay, so that's an issue that we have to work on differently. Okay, so let's go back. Okay, so that's basically this. And then next thing is, I look at the spectrum of the IF, it's very clean. There are no, from 950 to 2950, there's nothing. It's flat, just the noise. Okay, and the slope that is coming in from the IF amplifiers and filters. That's you're always going to get the slope but we're going to leave this out until we start circuit implementations where we would adjust with an equalizer, LC type equalizer to equalize this slope. Okay, here's just the IF section alone. Okay, and there's about 35 dB of gain in it, 30 to 35. So which means we have a slope of 5 dB, and that's unacceptable. Let's see what we are gonna what we are asked to design to. I'm going to go back to here. So the gain value, gain flatness, plus minus 2 dB. Actually, that's not bad. So we got about the maximum is 2.5 dB. Okay, but in any way, we really have to design in an equalizer to equalize it a little further. But it does give us. It seems like there is 5 dB of margin anyway. But we can't risk that we're going to fail that spec. Okay, let's see. This is okay. This is the convergent gain. Okay, throughout this system in here. So looking in, you feed in RF signal in here. That's between 12 gig to 22 gig, and I'm plotting the signal that I'm going to get out at this IF signal in here. So this x-axis in here, even though it's displayed with reference to the input frequency. You could display this with the reference of the IF frequencies, in which case this will be in here 0.95 gigahertz, and this will be 2.95 gigahertz. But the reason I do this, why I sweep this far down, is because I want to see the image in here. I want to see what is the image rejection, and that's really what you see in here. So you would want to put a marker on the highest gain in here, and this point in here, which is 15.3. That's my highest image at the low band frequencies. And of course, look at this. You can see the slope going down this way, a negative slope. This is going the other way. It's because the image band is always spectrally inverted. But you can see that it's pretty good. So we're getting 90-20. That's about 60 dB of image rejection combined between the front end filter and the signal sideband receiver. Okay. So next, what I'm going to do is the signal generator in here. I'm going to vary the input. All of this is done with the signal level in here is minus 90 dBm. So what I'm going to do is I'm going to sweep the power level, fix the frequency to the middle, okay, 18 gigahertz or so, and then sweep the power level and see the IF to see the dynamic range, and that's what I see in here. So we see that we're starting out from minus 90, somewhere out here, or minus 100. And then we're going to go out and it's going to start really saturating at about that marker 4, minus 55 dBm. Now, minus 55 dBm, you're really, unless you've got oscillation, unless you got interference directly coming into the lab while you're performing, testing this, there is no way that you can get a KE band at that power level, because the SATCOM signal is just, there's no way. Okay, so this is pretty good. So the dynamic range is beautiful. Okay, so the next I'm going to do is I'm going to come back to this here, and I'm going to sweep the front end in here and watch the gain and the noise figure, how it behaves, to see the out band response, how it does. And we do this with a sweep parameter for using the system view tool. So I'm going to sweep from 14 gigahertz to 25 gigahertz, okay, 100 points. And the sweep parameter that I'm going to do is the FRF low. And what that is, okay, let me just show you on the system view. So in here, system view